Okay, let's get started. Is Hoon here? Yeah, okay, great. So you're scribing, right? So just a recap from last time we met, last week. We're about to analyze index algorithm for estimating the LP norm of a vector x updated in the turnstile model in a data stream. And we used a linear sketching matrix that was filled with these p-stable random variables. I'll write the algorithm again in a second. So recap, we say that a distribution dp is a p-stable distribution. It's a distribution over real numbers. If you take n independent random variables from that distribution and then take sum over I, zi, xi, x is a fixed vector, that should look like itself a p-stable distribution, but scaled by the LP norm of x. And these things exist if and only if p is between 0 and 2. If p is less than 1, then LP is not a norm, but it still has that scaling anyway, okay? And you might wonder, how do you sample from these distributions, or what do these distributions look like? So there's no closed form for the density function of a stable distribution, except for special cases, like p equals 1 has a special form, p equals 2 is the Gaussian, has a special form. But I think none of the others do. However, there's a statistics paper in the 70s that showed how to sample from a p-stable distribution. Okay, so don't worry about why this formula does it. The only thing I want to say here is if you take two uniform random variables, if you sample two uniform random variables, you can use them to generate a p-stable random variable. Okay, that's the only takeaway from that ugly-looking formula. So you can actually generate them. Okay, and this distribution you get out here, remember I said that I wanted it to be scaled such that if you look at this distribution dp, it looks something like a bell curve, just like a Gaussian, but it's heavier tailed. I wanted to say that if you look at the amount of mass between 1 and minus 1, it has half of the mass. Okay. That thing has the p. So if you take any p-stable random variable and scale it by any fixed constant number, it's still p-stable. So this thing is p-stable. It doesn't quite have this property. It's going to be some other. It's not going to be 1. It's going to be some other number where the halfway point is. But imagine taking that random variable and scaling it so that it has the right median. Okay. So I'm going to assume that half the mass is between minus 1 and 1. Okay. So index algorithm was you take the matrix pi, your sketching matrix, to look something like this. Okay, where dij, or sorry, pi ij is a p-stable random variable. This means distributed as a p-stable distribution. Okay, so we're going to take y equals pi x. M is going to be something like 1 over epsilon squared. And we're going to estimate xp as the median, where 1 goes from I to m of yi. Okay. So that's the algorithm. That's what we talked about last time, and now I want to analyze it. Any questions about what the algorithm is? Okay. So let's analyze this algorithm. Okay. So I'm going to let and also, let me just some notation. Very good. Actually, let's. I'm going to let IAB, okay, be the indicator function of the interval AB. So this is equal to 1 if this is a function. It's 1 if x is in that interval and 0 otherwise. Right? Now, what's the expectation of the indicator function of minus 1, 1 applied to yi over the LP norm. What is this thing? First of all, what is yi? What kind of random variable is yi? How is it distributed? dp scaled by the LP norm, right? yi, each entry of y is, like the ith entry of y is the ith row of pi dotted with x, which is a dp scaled by the LP norm of x, right? This thing, let's say that the rows of pi are these vectors. I'll call them z1 up to zm. So this thing right here is just zi dotted with x over the LP norm. So this is dp right here. This is distributed like dp. So this is a half. Right? That's what that scaling means. Okay. Now, tell me, what is the expectation of the indicator function of -1 minus epsilon, 1 plus epsilon, applied to yi over the LP norm? What's this expectation? You can tell me up to thetas or whatever. I want some handle on this. And you don't have to be too rigorous. Just assume that this is what the density of a p-stable distribution looks like. Okay? So what does this mean? What's the expectation of the indicator function of this interval on this? It's just asking how much mass is between -1 and 1. Right? And now what I'm asking is, if you just stretch out the interval by epsilon, and then add in this extra mass here, right? What's the new expectation? Yeah, it's a half plus theta of epsilon, even. Right? Because, let's say you went out to the number 2, right? And you went out to the number -2. So I'm being a little non-rigorous here. It's known that this distribution really is bell-shaped in that when you go away from 0, it decays. Okay, the PDF decays. So if you go out to 2, what's the PDF? It's some number. Call it c. And if you go to -2, it's that same number c. So in particular, for any epsilon between 0 and 1, the PDF there is at least c. So if you move out by epsilon, you're gaining at least c epsilon mass. Right? What I really want to say is not just O of epsilon, but really omega epsilon. I want to say that you really are gaining roughly epsilon mass if you move out by epsilon. And similarly, what happens if you shrink the interval by epsilon? Right? What's this? Half minus theta epsilon, right? So now let's look at the random variable. 1 over, let's look at this random variable. 1 over m, sum I goes from 1 to m, of the indicator function of -1 minus epsilon, 1 plus epsilon, evaluated at yi over the LP norm. So what does this random variable mean? Someone interpret this in words. Yeah, so the average of that thing, but basically, so what do I want, right? What I want at the end of the day is that the median of these yi's is between 1 minus epsilon and 1 plus epsilon times the LP norm. What this expression is telling me what fraction of the yi's gave me a value less than 1 plus epsilon times the LP norm. What fraction of yi's give me yi is at most 1 plus epsilon times the LP norm? That's what that's counting for me. And the expectation of this thing, we just calculated it by linear to expectation. It's a half plus theta epsilon. Right? So in expectation, more than half of the yi's are giving me a value less than this. Okay? Similarly, in expectation, if you look at this expectation, right, this is what we just calculated on over there. This is here the fraction of I is giving me yi is less than or equal to 1 minus LP norm. Right? So what this is telling me is more than half of them are less than this threshold in expectation. Right? And less than half of them are less than this threshold in expectation. So if both of those things actually happened, the median would be in between these two thresholds. The median of the yi's in magnitude would be I should really, yeah, okay, good. The median would be in between these two thresholds, which is exactly which exactly means that my algorithm is correct. Right? Okay, good. But this is all an expectation. I want to say that not only are these expectations correct, but there's actually a decent chance that more than half are below this threshold and less than half are below this threshold. And the usual way we say that things happen like the expectations tell us they will is to use Chebyshev, which requires us to bound the variance. Right? The variance of this random variable and the variance of this random variable. Okay? Now, the variance of 1 over m times the sum of over I of the indicator function of minus 1 minus epsilon 1 plus epsilon of yi over the LP norm. Okay, so there are a bunch of random variables we're adding together, and there's also a scale factor. If you scale a random variable by c, what happens to the variance? You multiply by c squared. So this is equal to 1 over m squared. And then if you sum a bunch of independent random variables, their variances add. So the variance of this sum is the same as m times the variance of one of them. So times m times the variance of one of them. Okay, so the variance of an indicator function of this p-stable distribution looks a little bit complicated to me. Okay? But this random variable right here is always either 0 or 1. Right? It's the indicator function applied to something. It's always 0 or 1. Its variance can't be bigger than 1. Right? No matter what the distribution of that thing is. The variance of this can't be bigger than 1. So this thing is at most this, which is 1 over m. Okay, so we know what the expectations are. We get that the variance of this is at most 1 over m. The variance of this is at most 1 over m. So the usual Chebyshev analysis will tell us that if you choose m to be something like 1 over epsilon squared, you'll get 2/3 success probability. And that's the end of the proof. Yeah?
Would you get a stronger guarantee if you use the turn-off bound? Or why, I guess the question is why not use the turn-off bound here?
Oh, why not use the turn-off bound? Let's see. Yes, that is right. Yeah, you're saying, I think what you're saying actually might be correct. So basically, you can choose m to be something like 1 over epsilon squared times log 1 over delta, and then directly apply the turn-off bound, and then get success probability 1 minus delta. That sounds reasonable to me. That sounds reasonable to me. Yeah. Or you could do, you could do that. You could do the median of medians, which is useless here. I mean, it's basically, you could do what you said instead. Just take the median of more copies. Okay. So good. Now there's still one, big issue with this. Okay. Oh, yeah.
So can you explain how that equation maps to what fraction of yi's give less than that? Like how that maps to the equation?
Okay, so that indicator function, for that to evaluate to 1, right? Its argument has to be in the interval. So yi over the LP norm has to be in that interval. And just moving LP norm to the other side means that yi has to be between, or if you want to think about it like that, maybe this makes it clear, I don't know. This is the same thing as if I put an absolute value of yi here and made that a 0. Right? So for this indicator function to be 1, it means that this thing had to be less than 1 plus epsilon, which means that the absolute value of yi has to be less than 1 plus epsilon times the LP norm. Yeah.
If I understand correctly,
Yeah.
the constants implicated epsilon depend on p.
They depend on p. That's right. Yeah. So yeah, the constants hidden in this theta epsilon will come up when you try to actually apply Chebyshev, right? Because the expectation here is this half plus theta epsilon, and that constant is related to how small can what is the PDF at the number 2, for example? How small can the PDF get at 2? Yeah. So.
For example, if p tends to 0,
Yeah.
this constant would really, like, this theta of 1 over epsilon squared would really go to infinity.
Right, yeah. So that's right. As p goes to 0, this constant blows up, or I guess shrinks, which means that you need more rows. That's right. Yeah. So I didn't, you can do some analysis to get explicit bounds on the PDF at various points, which tells you what that constant should be. But that's really just a bunch of math that I don't want to get into, and is beyond the scope here. If you really want to know, I did those calculations somewhere in my thesis, and I can put a link in put a reference in the notes when you send them to me. Very good. So there's still one issue, which is the following. Okay, so we could have done turnoff like you said. If we do variance, recall that, so we have this matrix pi, right? Here it is. Pi's right here. Here's the first row of pi, the next row, the last row, et cetera. So where did we use independence of the entries of pi? Right? So if you fix a particular row, we really needed that the entries of that row were independent because we wanted to say that yi is a p-stable random variable. Right? That p-stability condition depends upon these zi's being independent. Right? The entries in the row need to be independent to invoke to say that yi is actually p-stable. So we know that within a row, the entries need to be independent. How about between rows? Does this row need to be completely independent of all other rows? Should all the rows be drawn independently? Huh? Yeah, the rows actually only need to be pairwise independent. Right? So if you imagine that there's some random seed that generates a row, and each row has its own random seed, those random seeds just need to be pairwise independent. Okay. I mean, I haven't talked about, so this is a continuous distribution, so it's a little weird. You might ask, how do I generate pairwise independent Gaussians or pairwise independent Cauchy random variables, et cetera? So what you're actually going to do, and I don't want to get into precision issues, what you're actually going to do is say that this argument would work if actually you didn't draw theta uniform in that interval, but you did this. So let's say this is minus pi over 2, and this is pi over 2, right, which is your theta. Just like discretize this interval very, very, very finely. Okay, and you're not going to draw an actual uniform random continuous number. You're going to draw one of these discretization points uniformly at random. And the same thing for R. So now really you're picking, kind of random discrete points in this set. That's things that we know how to do using polynomials, for example. Okay. So I don't want to get into that, but if your discretization is fine enough, you can prove that you won't, you'll still be within epsilon of what you should be. Okay, basically the amount of precision, needs to be like log of n over epsilon or something like that. Okay, but good. So that means that we can generate each row using just kind of uniform numbers from sets like this. And then across rows, those seeds need to be pairwise independent. But there's still the issue that we need each row to be fully independent. The entries in a row need to be fully independent of each other, right, in order to say it's p-stable. But actually, we don't really need yi to be p-stable to make this argument work, right? What we really need is, suppose kind of wi were the sum of qij, xj, where these are only, ky's independent, p-stable, right? So imagine that we replace the entries in a row not with fully independent p-stable random variables, but ky's independent ones. And what we want that the expectation of the indicator function of AB evaluated at yi over the LP norm is basically the same, let's say up to an additive epsilon, as the expectation over the indicator function of AB of yi over LP norm. Right? If we could prove this, if we could say that, what is this really saying? This is saying that if you had used ky's independent p-stable random variables, then the amount of mass in any interval is basically the same as if you had used fully independent p-stable random variables. If you could show this kind of claim, then you could still invoke the same exact proof. Okay? And this thing happens to be true for k being at k as long as k is at least something like 1 over epsilon to the p. So this is something I showed with Kane and Woodruff. Okay, and right, so how many random bits do you need to store a ky's independent hash function? Mapping, let's say, n to n. K log n bits, right? So here you would need 1 over epsilon to the p times log n bits. But p is less than 2. So that's less than 1 over epsilon squared log n bits. You're already using 1 over epsilon squared rows in your pi to store y. And I said that the precision is also log n bits for y. So the space required to store this ky's independent hash function is actually less than this space. But that's just for a single row. You need one of the, you need that for every row. If you were naive and said that that seed is independent across all rows, then you would end up using 1 over epsilon to the p times log n times m bits, 1 for each row. And that would actually be a problem, because that would be bigger than 1 over epsilon squared. That would actually dominate this. But again, you only need the seeds across rows to be pairwise independent. Okay. So let me write this down. So you can specify using k times log n bits, right? So think of this as a number in n to the k. K log n bits you can think of as a number between 1 and n to the k, right? And what I'm saying is that that seed across different rows only needs to be pairwise independent. So what we actually want is across rows just need to use a pairwise independent hash function h, which maps a row into one of these numbers. Right? And this thing can be specified a number of bits, which is something like big O of the log of the max of these two numbers. Okay, which is not that much space. So overall, this entire random matrix can be stored in something like k log n bits. So yeah, I want to make sure that this. Maybe you're not used to seeing these kinds of arguments with pseudo-randomness. By the way, there is a course at Harvard called pseudo-randomness, CS225. So if you want to play with pseudo-randomness even more, you can take that course. But are there questions about what I'm saying here? Okay. So ignoring the p-stable issue for a second, just imagine that this is a matrix of random bits for a second. Okay. What I'm saying is each row of that matrix can just be k-wise independent, and we know how to generate k-wise independent random bits, n of them. It takes k log n bits for your hash function. So the description of the hash function is a k log n bit number. Think of it as a number. Think of it as a number that's roughly n to the k. Okay? It's actually O of k log n bits, so it's actually going to be n to the O of k, but whatever. And now what we want is that each one of these rows has an associated n to the O of k number, right? So we just need a pairwise independent hash function. Okay, so good. Okay. So I'm not going to prove this in class because it's a bit of a pain. But I'll show you, and this is something that we did after index algorithm. I want to show you how Indic himself analyzed it. And it's going to lose a little bit. It's going to lose an extra log n factor in the space, but it's a general technique that you can use for lots of problems. Okay, so okay, so how did Indic generate this matrix pi? So digression, de-randomizing branching programs slash space-bounded computation. Okay, so for the next 2 boards or so, forget about index algorithm, and I'm going to show you something about space-bounded computation, and then we're going to apply that to index algorithm. Okay. So I want to introduce something called a branching program. A branching program is, think of it as like a grid graph. Okay, so there's an initial node on the left all by itself, and then there's a grid. Okay. And the number of nodes in a particular column is 2 to the s nodes. I'll say what s means in a second. And let's say that the number of layers, the number of columns is r. And each node has some out edges. And there are 2 to the s out edges. Okay, so what does all of this mean? By the way, just out of curiosity, who's seen branching programs? Okay, so most haven't. That's fine. You will now see them. Okay, so what should you view this as being? So it represents a space S algorithm, right? And you start at the left node and repeatedly read in the next S bits of input. Okay, so you have some algorithm that uses space at most S. Your algorithm starts in this state. Okay? You read in S bits of the input. So this graph is the description of a program. And there's some input that's written here. So there's S bits here, there's S bits written here, there's S bits written here, etc. So there's a bunch of bits chopped into chunks of size S written at the top. You read in these S bits, and then that causes you to go somewhere in the next layer. It might be that two different S-bit strings make you go to the same place. So the degree here is 2 to the S because that's the number of S-bit strings there are. Think of this as like a finite state machine, right? You read in S bits. There are 2 to the S possibilities for that. You go to a new node. From here, you read in S bits. That takes you to a new node. You read in another S bits. That takes you to a new node, et cetera. At some point, you'll end up somewhere in this last column. That's your final state. Okay? And what we're going to be focused on to apply to index algorithm is ways of feeding in. So imagine that these, RS. So imagine the input is a uniformly random in 0, 1 to the RS. The input is a uniformly random bit string of length RS. Okay? That's going to induce a distribution on the output states. What I'm going to be concerned with now is how many bits do you need to generate this top layer R times S bits? You need R times S random bits to generate this top layer. My question is going to be, how can we generate RS bits using fewer random bits such that the output distribution of this branching program will still be very close to what it had been if we had fed it truly random bits? Yeah?
So in between like the first layer and the second layer, does the input on the first layer matter to where it goes the second? Because that would make 2 to 2s simple, right?
So when you're in any given column, you're at some node. You don't remember any of your history. All that matters is like, where are you right now? And then where you go just depends on the next sequence of S bits. I don't know if that answers your question.
Okay, so there's no like the branching is like if I'm here and I'm here,
Yeah.
they both go to the same place at the same time.
Oh, you mean if you're here versus you're here?
Yeah.
No, those can have different edges coming out of them. The way that this interprets the S-bit chunk versus the way that this would deal with the S-bit chunk can be totally different. The edges don't have to look the same at all. Yeah?
You just care about the final state, or you care about distribution as well?
I'm only going to be concerned with the output distribution on the final column. So I'm imagining that this entire top string written down of RS bits is my input. And what I'd like to say is, if I feed this code, this program, okay, if I feed this program a totally random input versus a pseudo-random input could mean the evaluation of a hash function or something. It's still going to behave in the same way, meaning its final state is going to be almost the same. The distribution on the final state is going to be almost the same. Okay. We want similar distribution on output states using many fewer than RS random bits. Okay, and then we're going to use a result of Nisan, so theorem, let B be any branching program as, as over there. Okay. And F mapping 0, 1 to the S to 0, 1 is some function, is any function. Actually, okay, so let me write and then I'll say something. There exists a hash function, okay, H, which, well, he calls it a pseudorandom generator, mapping 0, 1 to the, let's call it T, into 0, 1 to the RS, for T being O of S times the log of R over S, such that the probability that F of the probability over X uniform in 0, 1 to the RS of F of X equals 1 minus the probability of Y in 0, 1 to the T. Sorry. And so let me parse this. So, sorry, one thing I should say about these quantifiers is there exists H should have really been the first thing I wrote. So there exists an H such that for any branching program with parameters S and R, and for any F, this holds. Okay, so there's a single function H which takes as input T random bits and stretches them out to RS random bits. Okay, so it takes T random bits and stretches them out to RS. Notice that you should think of S as being very small, like log n. We have a log n space algorithm. And R is something big, like R is like polynomial in n. So then, in that case, T is stretching S, like log n times log n, log squared n random bits into like into n random bits. So it's like almost an exponential expansion of the randomness. Such that, so think of F as a statistical test. F is some function, is some statistical test you're using to distinguish, was B really fed a truly random RS bit string, or was it fed the output of Nisan's H? What it's saying is no matter what statistical test you use, the probability that your statistical test can actually distinguish the two is very small. Right? If you feed your branching program a truly random X versus feeding it the output of Nisan, the probability that your test flags it, is the difference is very small. It's 1 over 2 to the S. S is like log n, think. So this is like 1 over poly n probability that you'll be able to distinguish the two. Okay? Questions about the statement of this? Yeah. Yeah. Oh, right. So the probability that you're equal 0 is just 1 minus the probability that you're equal 1, right? So the fact that this is true is also the same for the zeros. So yeah, think of like F spits out 1 if it thinks it's Nisan, and F spits out 0 if it thinks that it's uniform, right? And it's saying that no matter what your F is to distinguish the two, you're not going to be able to distinguish them with good probability. No, so yeah, that's what I meant to. H does not depend on the branching program. So there exists an H such that for all branching programs and for all functions f, H fools them. Yeah. Okay, good. So I'm not going to prove Nisan's theorem. I'll tell you what H is. Okay. If you really want to see the proof of Nisan's theorem, you can read his paper. But I'll tell you what H is. It's something. It's not a complicated H. People usually call a pseudorandom generator a PRG. So what does it look like? So we're going to build a perfect binary tree. The height of this tree is going to be log base 2 of R over S. Okay. Let me make these circles a little bigger. We're going to pick here, each node is going to have a value written in it. The root node is going to have a value z, which is just uniform in 0, 1 to the s. Okay, it's going to be a uniform random value in 0, 1 to the s, random s-bit string. And every layer, there's going to be a hash function. Let's call it h1 is the first level of the tree, h2 is the second level of the tree, up to h log of r over s. Okay. And if you go left in the tree, the node just copies its parent's value. If you go right in the tree, you apply the hash function at your level to your parent. So here you apply h1 to the parent. So here you have h1 of z. Here you copy the parent because it's a left child, so you have h1 of z. Here you apply h2 to the parent. So here you have h2 of h1 of z. And each one of these is a hash function mapping 2 to the s into 2 to the s, and it comes from a 2-wise family. You pick h from a pairwise independent hash family. You pick h2 again from a pairwise independent hash family, but independent of h1. So these are independently chosen pairwise independent hash functions. How many bits does it take to specify h1? S, right? A pairwise independent hash function from q to q takes like log q bits to represent, O of log q bits. So this takes O of s bits to represent, this takes O of s bits to represent, et cetera. The total number of random bits that you need to specify. So what is h? H of z is the concatenation of all leaves. This is the first s-bit chunk that you feed to the branching program. This is the next s-bit chunk that you feed to the branching program, et cetera. So each one of these is of length s. The number of leaves is r over s. So you have, I guess really you need log r. Maybe I should have said. Log r. So you have your rs random bits, okay? And the total space to store so h takes as input. You should really think of h as taking as input. It takes as input z, but it also takes as input descriptions of all of the hi's. So this is S bits, and each one of these is S bits, and there are log R of them. So the total number of bits you need to specify to feed into H is S log R, O of S log R. I'm not going to analyze this, but this is the scheme. Questions about the scheme, what it is? Yeah. Yeah, so this is basically Nissan. What Nissan provides us is a pseudorandom generator for branching programs. These are called read-once branching programs, which is related to pseudorandom generators for space-bounded computation. Because if you have space-bounded computation, you can represent that computation via such a branching program, right? Where every node, so basically in this way, right? Your algorithm starts in a certain start state, and then you imagine that it can read S bits at a time. S is its own space. It can store S bits, right? So let's say it's a 2S space algorithm. It has S bits of space. It reads in the next S bits, and then it chooses to go somewhere. Technically, this model of computation is a bit stronger than space-bounded computation, because I'm not assuming, right here I'm just assuming that these transition functions can be arbitrary. But if you think about it, the space-bounded algorithm can't do arbitrary transition functions. Its transition has to be computable in small space as well, right? But we're fooling something even slightly more powerful. Yeah.
So isn't the space bounded by S, but we're using S log R?
Right. So, yeah. So we have a space S-bounded algorithm, and what we're saying is if there's that algorithm is here, there's someone outside of the system who's feeding inputs to this thing, some more powerful person who has space S log R at their disposal. If that person instead feeds in the output of Nissan's generator as opposed to feeding it truly random bits, this algorithm will roughly behave the same way. So that's what we're saying here. We're not relaxing the space bound. We're just saying, originally, this thing had an input of size RS, right? It can't store RS bits either. We're just imagining that there's some tape written in the sky that has the input. In any state, we're only using S bits. That's right. So
Space bound algorithm. Well, let's just say he's trying to do another pseudo-random input, that is another algorithm that is different. So inside a space algorithm, you only use S bit, but outside of that, you use that to generate a pseudo-random thing.
yeah, there's like an algorithm, and then there's someone else who's feeding input to that algorithm. So what I'm saying is that person who's feeding input to the algorithm can use S log R bits and still get roughly the same behavior. Okay, so good. So that's all I wanted to say about the workings of Nisan and what it gives you. Now I want to tell you how you can use Nisan's generator to generate pi. Okay? I want to say that if you generate pi using Nisan's generator, then index algorithm will still work. And what I'm going to do is I'm going to say that there's a particular branching program such that if you fool that branching program, Nisan's algorithm will work. That branching program is not going to be Nisan's algorithm. It's just going to be something as a tool in the analysis. If we fooled it, Nisan's index algorithm will work. So let me just describe it to you. So consider the following program. One, initialize. So let me write it like this. pi goes from 1 to m, and let me also say, let's say low is 0 and high is 0. Okay? For I equals 1 to m, initialize cur to 0. And then for j equals 1 to n, I'm going to say cur plus equals pi ij times xj. So think of the input that's coming in as being the first. Okay, so what's coming in as input to the branching program is the first row of pi, followed by the second row of pi, followed by the third row of pi, etc. And then we say if cur is less than or equal to 1 plus epsilon times the LP norm, output or high gets incremented. And then also if cur is less than or equal to 1 minus epsilon LP norm, then low is incremented. Okay? This is my branching program. So this is a space-bounded computation because this algorithm only maintains 3 counters, right? It maintains low, high, and cur. And low and high are each numbers that are at most m, so they take log m bits. Cur is going to take an amount of bits that's basically the precision that you need to store the pi ij, and then you're adding up n of them. So log n plus that, right? So in total, the space here is S, which is O of log n plus log m plus the precision. Okay, and I promise you that the precision you need is bounded so that this whole thing is like O of log n. M is less than n, right? So log m is less than log n. So this is a space-bounded algorithm. Okay. Oh, plus equals means increment cur by this amount. Like compute cur plus this and reassign it to cur. So increment cur by this amount. If cur is less than or equal to that, increment high. And also if cur is less than or equal to that, increment low. By 1. Yeah, increment by 1. Questions? Yeah.
So the curve brackets are after the iteration.
They're after this for loop. Yeah, but they're inside the for loop over I. So tell me, what is high counting and what is low counting? At the end of this whole algorithm, right? What are high and low counting? Yeah, they're counting exactly that, right? I mean, here we divided by m, but if you hadn't divided by m, high is just counting how many people are less than 1 plus epsilon times the LP norm, how many of the yi's are less than 1 plus epsilon times the LP norm in magnitude, and low is counting how many of them are less than 1 minus epsilon times the LP norm. This branching program is basically mimicking the proof of correctness of index algorithm. Okay? So as long as high is bigger than m over 2, as long as high is at least m over 2, and low is less than m over 2, the median will be correct and index algorithm will be correct, right? And if pi actually were a totally random matrix, then this analysis that we have over here implies that this thing will be good with high probability, right? kind of at the end of running, the randomness coming into this branching program are these values. Okay? You can imagine writing this algorithm as a branching program, right? Where basically these chunks, this is like pi 1, 1. This is pi 1, 2, pi 1, 3, etc. When you're done with the first row, then you see pi 2, 1, pi 2, 2, etc. You're reading in the pi matrix row by row, entry by entry in that row. Okay? And this is just what's the state of your algorithm, meaning kind of what are the values of low, high, and cur. Depending on what those values are, you get, each one of these nodes corresponds to a different setting of those 3 counters. Okay? And what we're saying over here is there's a final distribution. If you had chosen a totally random pi, a truly random pi, there's a final distribution on those counters such that the probability that those counters are good for you is at least 2/3 or something. By good for you, what I mean is high is bigger than m over 2 and low is less than m over 2. Yeah. Yeah. So yeah, so this might be a little confusing. So this program knows x. X is sort of hard-coded into the source code of the program, right? So when we're writing down this branching program, right? Remember, the way that cur is being adjusted depends on xj, which means the algorithm needs to know xj. If you move back here, essentially what that means is the way these edges point to the next layer depend on xj. This is also what I meant by fooling this branching program is a little more powerful than fooling just space-bounded computers. Because these branching programs, these edges can be arbitrary. Right? These edges can depend on actually quite a lot of information, like the entire vector x. Clearly, a space-bounded program can't store x, but we can encode information about x in these edges. Okay? This one? No, I don't. No, not. It should be less than or equal to. Because look at this analysis over here. What I said was the number of people less than 1 minus epsilon is less than half of them. And the fraction of people less than 1 plus epsilon is more than half of them. So this branching program is really just mimicking this proof. Yeah.
So am I right to say Nissan's this procedure can fool any branching program just like that?
Yeah.
And why exactly is that branching?
So what I'm saying is we can create a branching program. So fix x, okay? And what I'm saying is we can create a branching program. That the branching program, let's call it b sub x, because it depends on x. We can create a branching program that implements that algorithm. Okay, so the initial node here corresponds to cur, low, and high all being 0. And then we read in pi 1, 1. That's going to affect cur. Then we're going to read in pi 1, 2. That's going to affect cur, etc. And then eventually we end the loop over j, and we're going to maybe adjust high and low. And then that's going to move us somewhere as well. Now we read in the next row. So you can so the number of kind of let's say that low, high, and cur each have q bits. Okay? So the total space of our algorithm is 3 log q. So the total number of nodes we need in a column is 2 to that, which is q cubed. So each of these columns has q cubed nodes in it, representing kind of what those counter values are. So R is going to be the total number of entries in the matrix pi, which is m times n. Any other questions? Okay, so now we're basically done. Because if you fed this branching program, that branching program over there, truly random pi, right? Kind of some of these output nodes are good for us, and some of these output nodes are bad for us. Good for us means that high is bigger than m over 2 and low is less than m over 2. That's good for us. Bad for us is if that's not true. And what that analysis told us is that the probability that we end up in a good node is actually at least 2/3. And what Nisan tells us is, let f be the indicator function of the good nodes. Right? What Nisan tells us is the probability that you land up in a good node if you had used Nisan is at least 2/3 minus 1 over n or something. It's still very close to 2/3. So you're still succeeding with good probability. And what's the space that you need to feed into Nisan? It's going to be log squared of n. S log r for us, S is like log n, r is like mn, and m is less than n. So r is less than n squared. So S log r is like log squared n. So your final algorithm, okay, your final implementation of index algorithm would, on the side, store this. And then whenever you need entries in the matrix pi, it would generate them using Nisan's function h applied to this seed. So the total space would be like 1 over epsilon squared log n plus log squared n. So, if epsilon, for some range of epsilon, most of your space is dedicated to this part right here, to Nisan. So, this eliminates that problem, but it's a little more work to actually analyze KY's independence in this context, so I'm not going to do it. So that's index algorithm. Questions about index algorithm and this Nisan thing. So I encourage you to, if this Nisan thing isn't totally making sense to you right now, I encourage you to look over it a little more, because this is actually it's a very powerful way of de-randomizing streaming algorithms, or getting random bits for streaming algorithms, because you'll often be in a situation where you don't know how to generate pi. It'll be very hard to reason whether KY's independence works in maybe your situation, but it's usually easy to come up with a branching program that mimics the proof of correctness that says, if this branching program worked, my algorithm would have worked. Therefore, I can use Nisan. Okay? Okay. So if there are no more questions, this is p less than 2. Remember, p-stable distributions only exist for p less than 2. What about p bigger than 2? So I want to show you how you would handle that with a different algorithm. So the amount of space you need is something like, let's say, n to the 1 minus 2 over p times poly log n over epsilon space is necessary and sufficient. So the lower bound, there's an argument that you need basically n to the 1 minus 2 over p space. That's due to Bar-Yosef et al. I think that's the right reference. And then the fact that you can achieve this space was first shown by Indick and Woodruff. Okay, and kind of since the Indick-Woodruff algorithm, there have been several papers that try and simplify their approach, get rid of some log factors, get better dependence on epsilon. So today, we'll show algorithm of Andoni, and it's based on approaches of others. Andoni, Kraftgamer, and Onok. And Johari, Soglom, and Tardish. So yeah, if you can't find any of these references when you're preparing the scribe notes, just put a placeholder and I'll fill them in. I guess these I actually put the conference names. This one, it's like a manuscript on his website, so I can put the link to that. Okay, so I'm going to show you this approach of Andoni, which is based on these other papers. Okay. So, and today we'll focus on epsilon being like a constant. So I'm not going to get you a 1 plus epsilon approximation of the pth moment, of the p norm, sorry. I'll get you a constant factor approximation. And the proof can be modified to give you 1 plus epsilon. I might make there a p-set problem which says, show how to modify this to get 1 plus epsilon. Okay, you don't need too big of modifications to do it on the next p-set. But, so let me show you the algorithm. So again, it's going to be a linear sketch algorithm. So we're going to come up with the right matrix pi. And how are we going to do it? Pi is going to look like a product of two matrices. I'm going to call them P times D. P is going to look a lot like a matrix that you've seen, that you're going to see on p-set 1. Okay, there's a problem about a faster AMS sketch on p-set 1, and P is basically the same matrix. So each column of P has a random sign in a random location, and the rest of that column is 0. That's the matrix P. And the matrix D is a diagonal matrix. It's n by n. And each diagonal entry looks like 1 over u1 to the 1 over p, 1 over u2 to the 1 over p, etc. Where ui is drawn from the exponential distribution. Okay, and what is that distribution? X being exponential means that the probability that x is bigger than t is equal to 1 if t is at least 0, and e to the minus t for t less than or equal to 0. Okay, so the exponential distribution is such that an exponential random variable is always positive. Okay, and the probability that it's bigger than t is e to the minus t. And you're going to put a bunch of inverse exponential random variables on the diagonal with 1 over p's on the exponents. And p is going to look like that. So that's the matrix. Okay, so what you're maintaining is just this sketch. Of course, again, there's a lot of random variables here. You can't actually store them all. So you're going to argue that this is correct if those are truly random matrices, and then you're going to use like Nisan or something. Yeah.
What are the p's in the diagonal matrix?
What are the?
The one over p?
Oh, that's not b. That's u.
Oh, and the
So
rest
u is an exponential. Ui is an exponential random variable. This is a u. That's a u. U2.
and the raised to the power 1 over p.
Yeah.
And sorry, what is the p?
You want to estimate the p norm of the vector x. Okay, and so y is going to equal pi x, and we're going to estimate the LP norm of x as the infinity norm of y, right? Which is max of the absolute value of yi. Okay, and m. We're going to pick m to be something like n to the 1 minus 2 over p times log n. Okay. So why does this work? Is it clear what the algorithm is? Assuming that we can store these, big random matrices. Right, so you have m counters that you're storing, these entries of y, and then whenever you see an update to some xi, you multiply that xi by 1 over u to the ui to the 1 over p, and then you add it then you go to that column, and only one entry is non-zero in that column. You add it to that entry of y with a random sign multiplied by it. So the theorem is that the probability that 1 over 4 LP is at most y infinity is at most 4 times the LP is at least 11 over 20 or something. Something strictly bigger than a half. Right? So if you want to make that 1 minus delta, you'll take the median of lots of these estimators in parallel. So let's start the analysis. We won't have time to finish the analysis. Proof. How can we analyze this thing? So let z be dx. So y is pz. And the claim 1, is that the probability that a half LP is at most z infinity is at most 2 xp is at least 3/4. Okay. So the first thing I want to say is, if you had just applied d to the input matrix, right, and then just looked at the max entry of dx, that would already give you a good estimate of the LP norm. But you can't use that as your sketch because d has n rows. And I don't want to use n space. I want to use space which is like n to the 1 minus 2 over p. So first we're going to say z works with good probability, and then we're going to say that pz is going to still work with good probability. Does that make sense? So let's prove that claim. And then I think we're going to be able to prove this claim before class ends, and then we'll finish the analysis on Thursday. So proof of this claim. Let Q be the min of U1 over x1 to the p, U2 over x2 to the p, Un over xn to the p. The probability that Q is bigger than some value t is the probability that for all I, ui over xi to the p is bigger than t, right? Which is the same as the probability that for all I, ui is bigger than t times x to the p, t times xi to the p, right? Which is, these ui's are independent exponential random variables. This is equal to the probability over I of e to the minus t times xi to the p, which is equal to e to the minus t times the LP norm of x to the p. Right? So what I'm saying is that the min of all these random variables is actually an exponential random variable itself scaled by the LP norm of x to the p. Right? So this implies that the probability that Q is between let's say 2 LP to the p is equal to is this right? Okay, so this thing here, basically, this implies that Q is an exponential random variable divided by the LP norm to the p. Right? So the probability that Q is between these two things is equal to let me write it like this. Yeah. Let's say, let me put 1 over 2 to the p here. The probability that Q is between these two things is just the difference of the tail of the exponential distribution, which is e to the minus 1 over 2 to the p minus e to the minus 2 to the p. Okay. And if p is at least 2, you can check, using a calculator or something. This thing is always at least 3/4 using calculus. Right? But this quantity here is the same thing as the probability that 1/2 is less than or equal to 1/2 times the LP norm is less than or equal to z infinity is less than or equal to 2 times the LP norm. Right? The entries of z are xi over ui to the 1 over p. The entries of q are 1 over that, raised to the pth power. So the probability that this min is between this range is the same thing as the probability that this max is between these two ranges, which, because this is an exponential distribution, we can calculate explicitly, and it's at least 3/4. Okay, so we've shown this claim, and then now what I want to show is that actually y, the max entry in y will still be good with good probability. Okay, and then we'll do something else on Thursday.